Hello, everybody. This is Davide Falessi, and I'm very excited to be the session chair for ICSI for the session called Bugs and Repair. We have six papers, and we have five live presentation and one pre-recorded presentation. The first presenter is Wu Mingge from the Southern University of Science and Technology, Shenzhen, China, with the paper Simu Li, Detecting CUDA Synchronization bugs via memory access modeling. Please, Wu Mingge.
Okay, thank you. Hello everyone. Today our presentation is about how to detect synchronization bugs in CUDA program. So CUDA is the most popular GPU computing platform proposed by NVIDIA. And you can see the basic flow here. First, we start the application and we search for CUDA devices, load data from the devices, and we allocate the resource on CPU side and pass to the general function. And the basic idea is that it allocates resources on CPU side and execute kernel function on GPU side, and which is our target to detect synchronization bugs. CUDA enables a three-layer structure to manage threads, where multiple threads are managed by a block, and multiple blocks are managed by a group. As a result, CUDA needs a mechanism to synchronize different threads. CUDA enables barrier thin threads to synchronize block-wise threads, where thin threads waits until all threads within the same block has reached the executing command. We have an example here. The barrier function synchronization mechanism is to prevent a thread from executing unless all threads within the same block have all reached the same barrier function, as we can see here. When these three threads within the same block have reached the same barrier function, they proceed all together. We have three types of CUDA synchronization bug here. The first one is data race. The visit order for read and write action or write and write actions for two or more threads cannot be determined in CUDA programs, and we call this situation a data race. We have an example here. Suppose thread 1 writes something to the memory address, and the thread 33 writes something to the same memory address here, because the writing action cannot be determined in the order, so we say there's a data race. So for barrier divergence, when more than one thread belonging to the same block complete their task and leave the barrier while some other threads in the same block have not reached the barrier yet. We also have an example here. From line 1 to line 6, all these statements are within the if block, and thread 1 can reach this barrier function while thread 33 cannot. So we call this a barrier divergence. We fix this bug by moving the line 5 barrier function to line 7. For redundant barrier function, it is quite simple. A barrier function is redundant, no data race is triggered after deleting it. So we have a code sample here. After we deleting the barrier function at line 4, nothing happened, no synchronization bug. So we call this barrier function is actually redundant. So there are multiple automatic detection approaches for CUDA synchronization bugs, but some of them are heavy weighted. Because they're based on SMT solver and they actually need the devices to run, or they're limited bug types. For example, they can only detect data race or detect data race having their memory. So can we build a lightweight approaches for automatically detecting multiple CUDA synchronization bug types? Here is our tool Simu Li. We designed two components for Simu Li. One is input generation part. It takes LVM bytecode, which sliced by memory relay instruction as input. Then it takes evolutionary programming to find input that can trigger more memory conflicts to expose the dangerous parts for the detection part to construct memory model for detecting. In the input generation part, we need a finish function to shoot each solution in order to get the optimal. The finish function is defined as follows. And this function takes dimension and argument as input. Function gi refers to a function that returns 1 when the ith memory address is accessed by any thread and returns 0 otherwise. And fi returns the number of threads that access the ith memory address. So the star in N denotes the memory access range. And we can see the smaller the Phoenix function is, the higher chance the memory access conflict takes place. So here is our mutation part. First, we're mutating arguments. Tracing and mutating memory access related arguments for deriving the optimal solution. We can see an example here. We can see the variable stride, and actually the stride have influence on memory access. We can see here. So in case the optimal solution is close, we generate offset by normal distribution and add to it. And in case the optimal solution is far, we generate offset by quasi distribution and make a little far step to it. So we follow a different strategy when we're mutating dimensions. So here, this one is dimension, it's memory related dimensions. We can see the I and J can influence the memory access address. So we randomly generate a step vector ranging from -1 to 1, according to dimension size, adding it to the original dimensions. And we can see we only have X and Y here, so the Z dimension is kept to 0. In order to construct memory model, we had to define unit tuple first. So what is a unit tuple? Unit tuple is used to record memory access information made by a single thread. We can see here with the order. They indicate the thread with the order and thread ID, which thread it is, action, read or write. So a memory unit is corresponding to a single memory address, which contains multiple unit tuples. And the within order is increment by barrier function only. We can see here we have 3 unit tuples goes by order 0, when all the execution paths goes by a barrier function, and within order will increase by 1. The other adding to this memory unit will goes by the within order 1. So after we construct the memory model, we have some detecting policy. For the data race detecting policy, suppose we have phi I and phi j, and these 2 are unit tuples, and they sharing the same within order. They have different thread ID, and one of them has write action. And when the threads phi I and phi j are from different thread words, and we say it's a data race, actually we have 2 more conditions, and you can refer to our paper to get more detail. For barrier divergence, this one can be detected during constructing memory access model when there's any healthy thread after the ground execution is terminated, or 2 threads end up at different barrier functions. For redundant barrier function, actually we're grouping all the unit tuples with address within order to find out whether any data race can take place. If so, there's this barrier function is redundant. To evaluate the performance of CUDA, we conduct an extensive study that real-world project as our benchmark and comparing the performance between CUDA and state-of-the-art approaches. And we can see here, the identified bugs CUDA can detect 21 of them and fail 3 of them. It is better than any other approaches. And similarly, also can detect 24 previously unknown bugs other than other approaches. And 10 of them have been confirmed by the developers. We also have some replies from developers. You can refer to the paper to get more detail. So in summary, we propose the idea using evolutionary research to detect the synchronization bug and implement this idea to lightweight, fully automatic online detection tools. And this tool has to detect 24 unknown bugs, and 10 of them have been confirmed. And that will be all. Thank you.
All right. Thank you very much, Wu Minge. It seems
Yes.
there are no questions from the audience, so I can start my questions. The first question is, in slide 5, you have presented 3 different types of bugs.
Yes.
My question is about their frequency. So do you know whether they are all pretty frequent, those 3 types, or there is one type that is more frequent than another, and so more important? If you can go back to slide 5 so that
Okay. So in my observation, the most frequency bug is data race. There's many data race bugs, and the second one is the barrier divergence. And yes, here. And the redundant barrier function is actually, it is undercover. So in the previous approaches, we find that redundant barrier function is reported little by the developers because many developers, they are likely to add in the barrier function to prevent bad things happen. But in fact, many redundant barrier function is not necessary. It is redundant. So our tool has detected many redundant barrier functions, reported to developers, and the developers have confirmed by us. So from our observation from the existing benchmark, the data race bug is the most popular bug, and the barrier divergence goes after data race. And because redundant barrier function is really hard to find, so in the real world existing benchmark, we have only one redundant barrier function bug, but we find a lot of redundant barrier function in the unknown bug set. Thank you.
All right. Thank you very much, Wu Minge. I think time is over also for presentations. So I'm glad to present the second presenter, who is Giovanni Quattrocchi from Politecnico di Milano, with the paper fine-grained dynamic resource allocation for big data applications. Giovanni, we cannot hear you. If you can restart.
Yeah, sure. Sorry. So hello, everyone.
Yeah.
Can you hear me now?
Yes.
Okay, so our work is about big data batch applications, which are long-lasting assets, meaning that the same application is run multiple times with different datasets. So each execution of this kind of application could last several minutes or even hours. And the quality of service is defined as deadlines. So a deadline is the maximum allowed response time for a single execution of an application. And to run those applications, you usually use an ad hoc framework such as Spark. So Spark is the evolution of Hadoop MapReduce, and it provides a master worker architecture. So in the master is centralized, and in the master, all the applications are scheduled according to a certain policy. And then there are different workers distributed in a cluster, and each worker contains one or more executor. And an executor is a process that executes parts of the applications. So the resource provisioning in Spark is provided in three variations. So the first one, which is the default, is that all the resources are allocated to the first application in a FIFO queue. Of course, this is not enough in several cases. And in the second option, you can statically pre-allocate a certain amount of CPUs or memory to each executor. So you can say that you need 4 executors with a certain amount of CPU and a certain amount of memory. Third, you can also have a dynamic allocation, which is based on timeouts, which are defined by the user. So in general, the users must guess indirectly or directly the resource needed to fulfill a deadline. And in Spark, there is no notion of deadline. So it's everything is indirect. So there are 2 problems. So the first one is that we need to allocate the minimum amount of resources to fulfill a deadline, which means optimize resources. And also we have to consider that we can have parallel applications running in the same cluster and prioritize them according to a certain strategy. So for this reason, we present dynaSpark. So dynaSpark is an extension of Spark. We actually modified the Scala core of Spark, which is based on 4 levels of control. At the beginning, with dynaSpark, the user can submit an application along with a certain deadline. And then there are these 4 levels of control. So the first one is centralized. So we modified the master node. And so the centralized planning exploits profiling data. So for each application, we have a preliminary phase of profiling in which we gather different performance indicator on each application phase. So a Spark application is executed in phases as in MapReduce. In MapReduce, you have only 2 phases. In Spark, you can have many. So for each phase, when an application is submitted, dynaSpark computes a local deadline. So given a deadline, we compute a local deadline for a single phase and an initial resource allocation. And we do this using an heuristic, a custom heuristic. Second, we have a decentralized layer of control, which is installed in each worker. And in fact, each executor is wrapped onto a container, let's say a Docker container, and equipped with a controller, which is based on control theory. And we use this controller to change, to actually vertical scale the CPU cores allocated to each executor. The set point of the controller is the local deadline. And we do that, and the control is carried out using as a reference the application progress. And the control period is equals to 0.5 seconds, so it's very fast. So third, we also take in consideration the priority of different applications. So given that on each worker we can have multiple executors, there could be resource contention. So we solve resource contention according to different strategies that are available in dynaSpark. And also we can accelerate or decelerate given the global goal that the user set, either minimize the deadline variations or optimize the resources. First, we also manage memory. In particular, we scale the off-if memory of each executor. And once again, this is done using an heuristic, and we vertically scale. So we scale at runtime without restarting any process. So for the evaluation, we extensively evaluate dynaSpark. Of course, here it's greatly summarized. So we use 8 benchmark applications, and we deploy dynaSpark in Azure. And the main metric that we use was precision. So how close we get to the deadline. And the closer dynaSpark gets to the deadline, it means that the fewer resources it uses, of course, without violating the deadline. And we tried different deadlines, different datasets for each applications. Also, we tried a different distribution of the datasets, even skew datasets. And on average, the precision was greater than 98%. That concludes my presentation. Thank you. If you have any questions.
Okay, thank you very much, Giovanni Quattrocchi, for your presentation. I see that there are no presentations from the audience, so no questions from the audience. So the question from me is, what is the impact of your results to practitioners? So how are you going to impact the state of the practice?
Well, actually, so ideally, we would like to contribute to the actually Apache Spark project, which is not really easy. This is the main goal. In general, I can say that our control system removes let's say some effort that each user must take into account in order to allocate resources. So we bring automation to this kind of applications, which are really not easy to manage. So on one hand is automation, and we would like to also contribute in the actual Apache Spark project.
Okay, thank you very much, Giovanni. And now it's time for the third presenter, Carlos Gavidia from University College London, with the paper The Assessor's Dilemma, Improving Bug Repair via Empirical Game Theory. Please, Carlos.
Okay, thank you. Can you all see my screen?
Oh, yeah.
Okay, great, brilliant. So good afternoon, everyone. My name is Carlos Goguryeo, and I recently graduated from the PhD in software engineering from University College London. And today I will present the paper I wrote my supervisor, published at the TSC Journal. So the problem we address is called priority inflation, and it was really well described in this book, Debugged by Paul Butcher. He mentioned that he was working on a bug repair team. They were under heavy workload, and because of that, they were only able to deliver fixes for the high priority bugs. Testers realized this, And they noticed that if they wanted a bug fix, they need to report it at high priority, even if it was in fact low priority. So testers started inflating priorities. The bug tracking system became inundated with high priority reports, and the development team was not able anymore to prioritize their work. In our paper, we posit that this is due to an incentive problem, and that this incentive problem can be solved with game theory. Game theory studies scenarios where rational and utility maximizing agents, called players, interact in scenarios called games. So let me show you how can we approach priority inflation with game theory with a small example. What you're seeing on the screen is a payoff table that's modeling a game between two testers, Alice and Bob. In this simplified game, they only have two actions: to honestly report priorities or to inflate. In a payoff table, we need to include the utility that each agent or player will obtain as a function of their actions. And let us assume that Bob and Alice get a monetary bonus when they get a bug reported and fixed. So, for example, in the top right cell, we see that when Alice is honest in their prioritization and Bob inflates, Alice obtains $100 while Bob obtains $150. This payoff table can be later processed by an equilibrium calculation algorithm to obtain the behavior of the players at equilibrium. So in game theory, behavior is defined in terms of strategies, and a strategy assigns a probability to each one of the actions. For our small game here, we're seeing that at equilibrium, Alice and Bob have the same strategy. And in their strategy, they inflate priorities with 100% probability. So we can conclude from that that the team where Alice and Bob work is susceptible to priority inflation. So in our paper, we apply the same analogies, the same techniques to prioritization process already available and adopted by industry, where we focus our work in two styles of prioritization. The first one is what we call distributed prioritization, where the person reporting the bug also prioritizes it. And the other one is what we call gatekeeper reporting, when we have a third party that's in charge of assigning the final priority. The guy that we call gatekeeper, or that it's normally known in industry as a bug triage team. To build our payoff matrices, we adopted a game abstraction approach called empirical game theoretic analysis. According to empirical game theoretic analysis, the payoff values are obtained via simulation, and the simulation inputs, as well as the strategies to include in the model, come from a process dataset. As part of the paper, we built a bug fixing dataset for the Apache Software Foundation by mining their Git and their Jira repositories. So what you're seeing in the slide is the results of our equilibrium analysis. Each bar in this plot corresponds to an equilibrium, and we have assigned a color to each one of the strategies that we include in our model. The always in play strategy, that's red, is the strategy that we associate with priority inflation. In contrast, the honest strategy, in light green, is the strategy that we associate with immunity to priority inflation. If you see in the left, for distributed prioritization, the probability of the always inflated strategy is 100%. We obtain the same result with a gatekeeper that can only detect 50% of deflated reports. And we also obtain the same for a gatekeeper that can detect 90% of deflated reports. We also include in our paper an ideal gatekeeper that's able to detect and correct every inflated report. And in this case, we obtain multiple equilibria, 3 equilibria. However, in none of the scenarios we modeled, we have our desired 100% probability for honest reporting. So we conclude that industry practice, the ones we consider, are susceptible to priority inflation. So to address this problem, we propose a new style of bug prioritization called assessor throttling. In assessor throttling, like in distributed prioritization, the reporter also makes an initial assessment of the priority of a bug. However, later, the developer that's in charge of fixing the bug, after delivering the patch and spending some time working on the bug, he evaluates this initial assessment. And if he disagrees, he will penalize the offending reporter in the reputation ranking. And this reputation ranking will later determine which bugs got fixed and which bugs not. So our proposed accessor throttling has one key parameter. It's like how much penalty do developers will apply when they detect inflation. So we start our analysis being really conservative with a 3% penalty. But as you can see in the slide, with 3% penalty, we have a really high probability for the always inflate strategy. So we started increasing the penalty, and we noticed that for the scenario in the slide, with 10% penalty, we obtain honest reporting with 100%. So we can conclude that accessor throttling with an adequate penalty value is actually immune to priority inflation. Accessor throttling to work, it relies on the fact that developers should prefer to work on reports from honest reporters. And we need a tool to enable that. We developed this Chrome plugin called the Fed. And the Fed can connect to a Jira repository via its API. It can obtain all the open bugs, and it can also sort them via the reporter reputation. So the Fed is in GitHub. The code is really open, and we hope this plugin will enable software teams to adopt accessor throttling. So to conclude, in this talk, I have shown how to use game theory to diagnose an incentive problem and to remove it. We believe that, like priority inflation, there are more problems that can be approached with game theory. So we invite you to read the paper and use game theory to solve your software process problem. That's it. Thank you very much, and I'm ready for your questions.
Okay, thank you very much, Carlos. I cannot see any question from the audience. So my question is that it seems to me that you have evaluated industry practice about bug prioritization, but you have done it on open source projects. Yes. So my question is, could it be that your results are biased by the fact that you have used only open source projects? And so maybe in industry, they have a way to do it and it works in industry. You know.
So like the data set that serves as an input is a really key factor. So the style of book triage is adopted by industry, we know that, but we don't have access to their data. So like there's a possibility, and it's actually a really interesting question. If our technique also can work in industry settings, I like to believe that yes, but yeah, I need the data to back up this assumption.
Okay, thank you very much.
Thanks.
So thank you, Carlos. Our fourth presenter is Anil Koyunju from the University of Luxembourg with the paper Fixed Miner, Mining Relevant Fixed Patterns for Automated Program Repair.
Hello.
Yep.
Can you see the screen?
Yes, but not in the right way. I think this is the presenter view. I think you need to click. Yeah, this is good.
Okay. Hello, I am Anil Koyuncu. I'm a PhD student from University of Luxembourg. I'm going to present you our work we published in EMSC journal, Fixed Miner. So I start by patching. Patching is a common activity in the software development. It's generally used to perform add new functionalities, update the code base, fixing bugs, and so on. So since this activity is recurrent, we assume that mining fixed patterns from these can guide mutation operations for patch generation systems. Literature includes various approaches, even though these techniques are handy for discovering diverse set of bugs. The limited scope of the mining and the intractability of the fixed patterns remain a challenge to guide mutation operations in program repair. So in our study, we present the Fixed Miner, which is an automated mining approach to infer fixed patterns that can be easily integrated to other patch generation systems. So we start by collecting the patches from open source repositories. Then, in order to capture the full semantic and syntactic meaning of these patches, we leverage rich edit script. Rich edit script is a notation we introduce in the paper. It is based on the commonly used edit script notation. Although the edit script notation is accurate describing the changes in fine-grained level, it fails to describe the intended behavior of the patch since much of the contextual information is lost. So in order to address this limitation, we propose to enrich the edit script by retraining more contextual information. So it is done by reorganizing the edit script under statement nodes. The produced edit script, rich edit script, encodes the ASD node types of the change, the repair actions that are attached, the tokens that are involved, as well as the parent-children relation among the nodes. Then we build a threefold mining strategy to leverage the different information encoded in the rich edit script. And each turn we focus on a single information type. First, we start by mining the changes that are affecting the same ASD node types. Then we mine the changes using the same repair actions. And finally, the changes that are affecting the same code tokens are mined. A single mining iteration also consists of 3 steps. First, we build a search index to identify the changes to be performed. Then we compare them, and we finally cluster them. A cluster here contains a list of changes that are sharing a common representation. And finally, to infer the patterns, we resort to clustering. A cluster is qualified as a pattern when it's frequently observed. In order to assess our approach, we formulated these 3 research questions. First, we check the consistency of the clusters of our approach against manual dissection studies. Then we check the compatibility between the patterns that are found in the literature. And finally, we check whether our approach is effective in automated program repair. So I will only cover the last research question. So we implemented an APR prototype system where we use the patterns that are mined from FixMiner. We evaluated our approach on Defects4j benchmark and compared to other state-of-the-art tools. Overall, we find that we can able to fix 26 bugs correctly. While these tools generate several correct patches, they also generate many more plausible patches, which are not, however, correct. We study this phenomena. We find that FixMiner produces patches with a higher probability of correctness, which is around 82%. So the high performance of FixMiner, along with CapGem, which is also another context-aware tool, confirms our intuition about the code context is useful. And finally, we check the overlap of the patches that we generate in our system against all the other tools. We find that FixMiner can fix 6 bugs that are not fixed by any other tool. This also somehow confirms our intuition about mining different patterns that are not seen before. So we release our tool in our GitHub page and all the data to replicate it. So if you have any questions, I'm glad to answer.
Nice. Thank you very much, Anil, for your presentation. Again, I see no questions from the audience. My question is, since sometimes you provide an incorrect patch, can you provide to the user the likelihood of the patch to be correct? Can this be a future work, or you do this already? So instead of just fixing it, you will say, this is how I fix it, and this is how I feel I fix it well.
Yes, indeed, we did this in our FSC paper last year. It's called iFixer. So rather than sending the single patch candidate to the user, we decided to send like simulate at least 5 or 10 patches, and assuming that the user would select among them the patch that he would like to apply. And it seems that it is performing slightly better, because since we don't have a way to validate the patches 100%, because we are using the test cases that are available in the benchmark, and the benchmark may not be even complete, so we assume that user is the best way to validate the patch. So rather than using the test patches, we just rely on the regression test and try to see whether user can select a better patch among the candidates.
All right. So there are two questions from the audience. We're going to address one. How large are the patches that can be mined? In other words, will it work well on patches that are higher than 100 lines of code? So how does it scale with patches that are smaller or large?
Yes. So for the speed of the computations, we introduce some parameters that are limiting the patches based on the hunk size and the line size. So it's a parameter that can be configured. So for our experiments, I think we focus on 5 hunks and 100 lines. But it can cope. But since most of the operations are performed in memory, so I think if the computer has enough memory, I think this limit can be increased easily.
So you're saying that the only limitation is not in your approach, but it will be on the memory.
Exactly. So I tried with bigger limits. It's pretty slow, but it's working.
But you don't know if it will become less accurate for bigger patches. That could be.
I don't think so, because the rich edit script we extract becomes much complex. So if it is like a new function insertion constantly in the code, we would able to mine it, but then maybe it's not very readable or directly readable by the user. But eventually the rich edit script guarantees that the form is kept always in an accurate way.
Okay. Thank you very much, Shaniel, for your presentation and your answers. The fifth presenter is Paul Montin from Technical University of Munich, but he was not able to join us. So Sylvia Brau is going to share his video about the paper int repair, informed repairing of integer overflows.
Hi everybody, my name is Paul Montian, and today I will talk about int repair, a tool for repairing integer overflows and in C source code. This is joint work between colleagues from TU Munich, KTH Royal Institute of Technology, and Nanjing University. First of all, detecting and finding integer overflows in C source code is a hard problem. And as we can see in this example here, data is multiplied by 2, and potentially the result cannot be held in the variable result such that this can overflow. In a nutshell, our methodology is as follows. The source code is fed into our symbolic execution component. Overflow is detected, then a repair is built. The repair is then validated. Then we perform target automated repair. Another step, then we generate the code and we insert the repair in the original code. Then we recheck again if the repair was successful. In that case, we have a correct repair, the bug was removed, and we have an artifact which has no bug. Otherwise, the bug was not removed and the source code still contains the bug. In a nutshell, it's very important to understand how our tool selects the repairs. So as you can see in this example, statement is fed in, and depending on the operators and types, it selects from the number of currently repair which we currently have in our tool. As for now, we have more than 300 repairs, and the tool suggests then at the end the patterns which make more sense. The main idea of our approach is that we fuse fault localization and repair generation phases into a single algorithm via SMT solving, and the steps are based in determining the integer upper bound, generating an SMT constraint system, selecting constraint values, recomputing the bound checking constraints, determining the fault type, selecting repair pattern, as previously mentioned, determining the new constraint system, and generating the code repair. Further, in this picture, you can see how an integer overflow is repaired. In the left, at line 33 and 34, we have the original program. And if the user clicks on the bug icon, the middle image, then the source code will be surrounded by this if-else branch, which represents the code repair, which fixes the bug in this case. So with respect to our results, we use the largest integer overflow test suite from NIST, and we also synthesized more than 50 programs which have more than 20,000 lines of code. So with respect to fault detection effectiveness, we tested with all programs, and we were able in more than 2052 programs to detect all the integer overflows. And for the large programs, we had some timeouts. Further, with respect to fault removal, for all cases in which we successfully found the integer overflow, we were able to generate repairs which eventually resolved and fixed the bug. Further, with respect to performance impact, as you can see, for large programs which have 20k lines of code, the analysis time is under 10 minutes, which is very similar to other static analysis tools. The binary blowup is under 1%, 0.56%, and the execution overhead in average is under 2%, 1.57. Further, with respect to program correctness, we implemented here a number of steps and automation in our tool to verify that the repairs are correct, and we can testify that that all repairs are actually correct and preserve program behavior, the intended one. With respect to effectiveness, with respect to comparing our tool with manual repairs, we compared it with we performed a use case with 30 participants. Half of them had access to the tool, the other half didn't have the access to the tool, and we measured the timings and how accurate they found and repaired the bugs. And we can say in conclusion that our tool, so the group which used int repair, is 10 times more effective in finding and repairing a bug. In summary, we presented int repair, a tool for detecting integer overflow and generating repairs which are also validated. We tested with more than 2000 C programs and more than 50 large programs. Our evaluation shows that the tool is very effective in determining the location of the bug and repairing them. And in a control experiment, we could show that our tool is 10 times more effective than repairing the bugs manually. So thank you very much. And if you have questions, please go ahead. Thank you.
All right. So thank you very much for playing the recorded video. And if you have questions, you can still write these on the website, and then the question will be reported in Slack. And then Paul will probably be able to answer those questions. Now, our last but not least presenter is Li Yi from the New Jersey Institute of Technology with the paper DL-Fix, Context-Based Code Transformation Learning for Automated Program Repair. Please.
Thank you. Can you see my screen well? Okay, let me start.
Yes.
Okay, thank you. Hello, everyone. My name is Yi Li. I'm from New Jersey Institute of Technology. I would like to introduce my supervisor, Dr. Shaohua Wang, and collaborator, Dr. Ting Yuan from the University of Texas in Dallas. During the development of the software program repair, the program repair could always be a very time-consuming process, and developers spend a lot of effort on it to help reduce the workload of fixing the bugs. Many researchers focus on design automated program repair. We call it APR tools to assist the developers to do the fixing. There are two main kinds of APR approaches. The first kind is the pattern-based approach. That is the traditional way of doing the automated program repair. Researchers found that similar code often have similar bugs, and among the similar bugs, the fixes could often be similar. So the pattern-based approaches are designed to catch the fixing patterns from existing bugs and apply them on the similar bugs. But this kind of approaches have one key limitation, that the fixing patterns cannot all be predefined. Instead of defining the patterns, some approaches use deep learning techniques to learn the fixing patterns. But the existing deep learning-based approaches also have the key limitation that they cannot learn the correct code transformation in the right context. Let me explain the key limitation as follows. The existing deep learning model often use translation model to fix the bug in the buggy method. Some of them put the whole buggy method as input into the translation model to do the fixing. Because there are too much context in the input, the translation model may have the alignment problem, which lead to the fixes in the incorrect fixing locations. Some others put only the buggy code as input. In this scenario, there is no surrounding code context in the input, and with different code context, the same buggy statements may have different fixes. Based on the reason of this, the translation model may generate incorrect code fixes in this situation. To address the limitation in existing deep learning-based approaches, we introduce our new model DRFix with the following key ideas. Firstly, we designed the DRFix to identify the code transformation in the cross-bounding context. Secondly, we designed the DRFix to use surrounding context learning results to enhance the code transformation learning performance. Here, I would like to use a real piece of code as an example to explain more in detail. As you can see, in this piece of code, the buggy line is a line 10. The reason to fix this line is that there is already a try catch statement that can return error messages. It is not necessary to define one more variable, process P. Also, the method called run command requires 3 parameters and line 10 needs 1. We call the code fixes shown in the line 10 and 11 that in the red box as the code transformation, and all the other statements in the same buggy method in the blue box, as you can see, they are the surrounding code context. By using this example, we would like to introduce our approach overview. In our DRFix model, there are 2 different deep learning layers to learn the code context and code transformation. Firstly, we put all the code context shown in the blue box as input into the context learning layer to learn the weight that can represent the surrounding context. Then we use both the code transformation shown in the red box and the weight we learn in the last layer as inputs for the transformation learning layer. With the process of this, our transformation learning layer can learn both the code transformation information and the surrounding code context information together to generate a candidate patch list to do the automated program repair. To be more in detail, in the context learning layer, we have the buggy abstract syntax tree with the buggy subtree. By passing it through the encoder-decoder framework, we expect to get a fixed abstract syntax tree as a result. In order to learn the code context only without too much influence from the code fixes, we use a deep learning summarization tool to summarize the buggy subtree into a summarized node. By controlling the output to have the same structure as input, we get a corresponding learned summarized node that contains the surrounding code context information learned inside of the framework. We regard this learned summarized node as the local context weight vector and pass it to the transformation learning layer for further usage. Next, in translation learning layer, we use only the buggy subtree and the local context weight vector we got as input for the other encoder and the decoder framework, and the output would be the fixed subtree that could be a fixed candidate patch to do the automated program repair. To evaluate our approach, we come up with 3 research questions. Firstly, we would like to compare our DRFix with other state-of-the-art pattern-based PR approaches. Secondly, we would like to compare our DRFix with other deep learning-based approaches. And in the end, we would like to do some sensitivity analysis to evaluate the influence of all features in our model. We do the evaluation on 3 different data sets from existing works. In research question 1, we only use the defects4j to do the evaluation. And for research question 2 and 3, we also added box or jar and a bug fix to do the evaluation. We use the correctly fixed bug number as the evaluation matrix for the research question 1. And as for research question 2 and 3, we use the top K accuracy to evaluate. Here are the results for the evaluation. As for research question 1, our approach can be seen in the red box. And from this table, we can see that our approach can fix more bugs than most of the pattern-based approaches on defects4j. And even for the best performed pattern-based approaches like P-bar and SimFix, we can still generate comparable results with them. We are the first deep learning approaches can do the performance like this. And as for the research question 2, we compare our approaches with other deep learning-based approaches on all 3 datasets. The results shows that our approach can fix more bugs than the most of existing can fix more bugs than all the deep learning-based approaches by at least fixing 2 more times bugs comparing with them. And as for the research question 3, we use a traditional sequence-to-sequence model as the base model, and then we add our 2-layer model design and add some program analysis filters to evaluate which part can contribute most. Then from the results, we can see that by adding the 2-layer model, our approach can have 550 improvements, and the program analysis filters can also help improve about 109%. So as a summary for our research, we have talked about the limitation of existing deep learning-based APR approaches, and we design our own model DLFix to address these limitations. By doing the evaluation on different data sets, our model have improved to outperform all other deep learning baselines and can have comparable results with the pattern-based baselines. Because for now, our DLFix can only fix 1 statement box, which just very similar to other existing baselines in this area. So in the future work, we would like to expand our work to the multi-hunk and multi-statement box. Also, we would like to evaluate our model on more different kinds of programming languages. This is all about my presentation. Thank you for your listening. The questions?
All right, thank you very much. Again, there are no questions from the audience, but maybe they will come in a few seconds since there are a few seconds of delay.
Yep.
Meanwhile, again, ask you one question, which is similar to the previous question, which is about scalability. So, do you think how much your approach is scalable and can repair code of different sizes well?
Yes. So because in fact for now we are doing the fixes only on the 1 statement box. So even the project is big or the bugging method is big, then we are still focusing on that bugging line. So the size of the methods really only influence the process of learning the surrounding context, but the fixing part, I think there is no influence.
Mm-hmm. A question from the audience is, what challenges do you think would be faced by applying your approach to other languages such as C, C++, I could add Python since it's very different?
Okay, thank you for the question. I think the most challenging thing is that for now, because we all know that deep learning model requires a very huge data set to do the training, and also if the data sets do not really contain a lot kind of bug fixing, then the model is hard to learn different kinds of fixes. So when we transfer to a new languages, the challenge thing is that we always cannot find a very good data set to train our model. Then so when we do the fixing, we will the model cannot always generate the correct fix for that kind of bugs in different programming languages.
Mm-hmm. All right. I see another question. So I believe this answer concludes our session on bugs and repair. I would like to thank all the 5 presenters in person and also the 6 who was not able to join us. So thank you very much. I would like also to remind the audience that it is possible to continue the discussion with the authors and presenters in Slack. So I suggest that you ask them a specific question or other questions. Other than this, thank you very much, and see you in the next session.
Welcome everybody to session 825 on code analysis and verification. In this session, we're going to have 5 presentations. We're going to have a technical presentation and 1 new presentation. So just make sure to ask questions about the talk by adding them to a slide on the left, and you can basically upvote, downvote your questions. So, but please be active and ask questions. So our first presenter is going to be Manuel Benz. So we're actually going to show the recording of his presentation, but he's going to be available to answer questions after the recording is done. So the talk is Heaps and Leaks, How Heap Snapshots Improve Android Taint Analysis, and it is a technical talk. So we can start playing the video.
Hi, my name is Manuel Benz. Welcome to my talk about heaps and leaks, or how heap snapshots improve Android taint analysis. This work is a joint effort between these excellent researchers and myself. Taint analysis is a commonly used mean to find vulnerabilities in software products. It aims to detect sensitive data flowing from source to not so preferable sink. Static taint analysis usually yields a very high recall, but also oftentimes suffers from a comparably bad precision and scalability. In particular, the precision of static analysis of languages with dynamic dispatch usually heavily depends on the precision of pointer analysis. Recent research by Crash et al. Has shown that incorporating data from heap snapshots can be either used to increase the soundness of static pointer analysis by augmenting the static pointer information with the dynamic one, or to increase its precision by restricting static pointer information to the dynamic one. Heap snapshots essentially are records of dynamic pointer information at a given time of app execution. In our work, we build upon the work of Crash et al. By also investigating the questions: how client analyses are affected by the heap snapshots-based pointer analysis, how many snapshots are required to yield the best results, when should snapshots be collected during the application runtime, and last but not least, can we find a middle ground between high precision due to restricting the static pointer information and high recall due to augmenting static pointer information. For that, we designed the blended tainter analysis heap stem, where we use the pointer information from heap snapshots as upper bound for the pointer analysis of Java fields. Thereby, we trade off recall from the static model for increasing precision through restricting the static pointer information to only dynamically seen objects. Our design especially enables 3 different modes of execution: separate heaps, where multiple snapshots are used with independent analysis runs and the results of each run are merged together; merged heaps, where the heap data of multiple snapshots is merged together to gain a single, slightly over-approximated snapshot; and static fallback, a mixed mode where we fall back to static pointer information for fields for which we do not have any dynamic pointer information available. This mode is independent of the other 2 and can be freely combined with them. For our experiments, we took 49 of the 200 most downloaded Android apps from the Google Play Store. We manually explored the apps on our smartphones and took a heap snapshot after each user interaction with the app. Thereby, we gathered more than 2,300 heap snapshots. For our experiments, we needed a ground truth to compare against. Therefore, as part of our work, we proposed Droid Macrobench, a real-world taint analysis benchmark comprising 157 taint flows labeled for feasibility of 12 of the 49 apps, effectively yielding 79 feasible and 78 infeasible flows, which is basically 50-50. In our study, we asked and answered 4 research questions, which I am now going to discuss. First, how are the precision and soundness impacted by using heap snapshots as an upper bound for the static analysis? By measuring against Droid Macrobench, we found that using the separate heaps approach and the merged heaps approach, the results only vary slightly. Both approaches yield a very high precision, but for a huge cost and recall compared to the purely static analysis. Second, How do precision and soundness change when using the static fallback approach? Using the static fallback approach, where we take a static pointer information for pointers that are not present in the heap snapshots, we measured a precision of about 77% and a recall of 68% with the merged heaps model of all collected snapshots. This is an increase of about 26% in precision and a decrease of about 31% recall compared to the fully static approach. The static fallback approach thus yields a good trade-off between precision and soundness. Having more than 2,300 snapshots for 48 apps collected after each user interaction, we further propose the following heuristics to choose from those. First, where the first snapshot is taken after the app has started. Last, where the last snapshot is taken that was made during an execution. Unique activity, where the last snapshot conducted before leaving each Android activity is taken, and all snapshots. Looking at all data points, we can generally say that using heap snapshots in any of the proposed configurations increases precision and reduces recall compared to the pure static analysis. Looking at the results for merged heaps, it can be observed that taking more snapshots gives a better recall but also lowers precision compared to taking less. For the static fallback approach, the picture is a bit different. Here, unique activity performs better than taking all snapshots. We conclude that when and how often a heap snapshot is collected has an impact of about 16% on precision and 13% on the recall, with the best overall results being achieved with a single snapshot per activity and the static fallback approach. In our paper, we also inspected the impact of the different modes and snapshot choosing heuristics to analysis performance and resource consumption. We leave the details about this part to the interested reader of our work. To summarize, we proposed a new middle ground between precision and recall by using pointer information from heap snapshots and falling back to pure static information where no dynamic information is available. We introduced Droid MacroBench, a real-world Android app benchmark comprising 12 apps with 157 labeled taint flows. We investigated how heap snapshots should be incorporated in a static analysis and at which points they should be gathered. We found that if precision is critical, a single heap snapshot taken at the start of an app might be the strategy to choose. In case recall is critical, however, a purely static analysis or an augmented version still yields the best results. Finally, compared to the fully static approach, static fallback achieved the best trade-off between precision, recall, and runtime performance. It heavily reduces analysis time and memory consumption, and furthermore, it increases precision by about a third while losing less than a third recall on average. This results in the overall best F1 score of 0.77. Thanks for your attention.
Thank you for joining.
So thank you so much for the presentation. And it seems like we have one question posed by the viewers. So question is, can you tell us more about how you mitigate threats to validity involving the user interactions you created for producing heap snapshots? Do you want me to repeat the question?
So how we mitigated threats to validity when making the heap snapshots for each user interaction?
Can you tell us more about how you mitigate threats to validity involving the user interactions you create for producing heap snapshots?
Okay, so what we did is basically we traversed the apps, and if you needed an account to get the full functionality of the app, we made an account, and we tried to really make each interaction in the app you could make. So we have like full coverage of the app, but of course we don't have like all combinations of actions you could do. But I think we really have like a pretty good approximation of that. Let's say it like that.
So since we kind of have a feedback, hopefully it was enough, and I think it's, if it's not, if somebody wants to have more questions, definitely can follow up with Manuel. So, and we have time for maybe one more question. So my question would be, what's the overhead of like taking and recording those snapshots? So how expensive is it?
So taking a snapshot takes like about 3 to 5 seconds. So the device will be stuck at that point. So this will take some time if you take a lot of snapshots, like for one app.
Have better recall.
Yeah, sure. You will have better recall then, of course, if you take more. Yeah, and also it always takes a little bit of time to read those snapshots in the analysis, right?
So how long is it going to take to read snapshot, kind of parse it and
this will also take like let's say half a second per snapshot. So it's not so much, but if you read like 50 snapshots, this will take some time, but this generally is like neglectable if you compare it to the analysis runtime.
So when you take those, when you said you're going to have a pause for 3-5 seconds, do you think you actually affect the behavior of the program that you basically observation actually affects how program is going to execute and so on?
Okay, so I doubt that, because what we did is actually we made a user interaction and then we waited until the UI has settled and there was basically nothing happening.
Okay. So. Okay. Well, I think we're done with all the questions. So thank you so much, Manuel. Very nice talk. So the next presenter is going to, where are we at? Okay, so the next presenter is Martin Kellogg, and he's going to talk about verifying object construction. And once again, it's a technical talk. So please make sure to ask questions on slide on the left of this presentation. Thank you. So Martin, you can start.
Thanks, Elena. So today I'm going to talk to you about how to use the builder pattern with the type safety of constructors or verifying object construction. So on the screen, I've got an example of a class in a language like Java. And as you can see, there are 3 fields in this class, 2 that are required, the name and the ID, and 1 that's optional. That is the nickname. And the standard sort of object construction API, as you might imagine, it would be a set of constructors for this class. And we would probably write the 2 that are shown on the screen. That is a constructor with the 2 required parameters, and then another constructor that takes both the 2 required parameters and the optional parameter. And now I want to imagine what would happen if we tried to construct a malformed user identity. That is, one that's missing one of its required parameters. So suppose we leave out the ID. We'd attempt to call this constructor that only takes the name, and the compiler would helpfully tell us that this is a bad idea and would issue an error as soon as we compiled the code, and we would not do that. So this is really nice. So this is a really powerful ability that constructors give us. So that's the real strength of constructors. But constructors also have some downsides. So the programmer has to write each one of them by hand. And especially when you're considering classes with many optional arguments, that can take a long time because the number of constructors that you need is exponential in the number of optional parameters. So for example, in the user identity, we had just 1 optional parameter, but we still needed 2 constructors, 1 with it and 1 without it. And if we have more optional parameters, we'll need every possible combination. And finally, the arguments to constructors are positional, which can make it difficult to read code and inspires things like named parameters in Python. And so to deal with these problems, programmers sometimes use alternate object construction APIs like the builder pattern. On the screen, you can see an implementation of the builder pattern for the user identity example. And I want to point out that there are a number of, or there's an inner class here called the user identity builder with a number of setter methods, 1 for each parameter. So there's a name, an ID, and a nickname method. And each of those takes a value for that and then sets a field on the builder. And then finally, the build method is called when the object is actually constructed. And that takes all of the parameters that have been provided via the setters and actually constructs the object we wanted. And this leads to nice client code. So programmers who are using this class that we've written are able to write code like this, where they call the setters in any combination, in any order, in this sort of chained method call, and then call build at the end and get the object that they actually wanted. And this shows us the advantages of the builder pattern. Right? It's flexible and it's easy to read on the client side. And frameworks can also implement all of this boilerplate that I showed on a previous slide automatically. So the programmer doesn't actually have to write this stuff. People have built frameworks that do it. But then let's consider the situation, a similar kind of situation, creating a malformed object that I showed with a constructor that the compiler forbid. So suppose that we leave out the call to ID here. What will happen? Well, in the best case scenario, we're going to get a runtime error because the compiler has no notion of which of these parameters are required or not. And perhaps the framework might provide a way to specify which parameters are required or not. And then it can add a null check in its generated build method that says, if the ID wasn't provided, throw a null pointer exception when build is called. But that still crashes the program at runtime and is generally undesirable compared to a compile error. In the worst case scenario, there's no check for it, and we end up using this malformed object in some way. And depending on what the object is for, this could lead to serious consequences down the line. So imagining that the object is used for some sort of security critical purpose, leaving out the parameter might leave you open to a security vulnerability. And so this shows the big downside of the builder pattern. There's no guarantee at compile time that the required arguments have been provided. And this is one of the big problems that those who provide the builder pattern face. So at the bottom of the screen, you can see a number of a number of issues from the Lombok project, which is one framework for Java that provides the builder pattern. And there's a great quote from the lead developer of the Lombok project, where he says that they get this feature request every other week. And he really wished he could provide it, but he didn't know how. And so this leads me to the headline result of this work, which is that we have developed an approach that allows us to get this type safety, the same level of type safety that you would get from a constructor, while retaining the same code that you would use in the builder pattern, and therefore retaining its advantages, its flexibility, its ease of use for clients, and its automatic implementation. So I want to now give sort of a very high level understanding of the key insights that led us to this approach and how we actually managed to do it. So to do that, I want everyone to think about how we would implement an analysis for this as a type state analysis. So in a type state analysis, what we're going to do is construct a finite state machine that encodes the property that we need to show. So in this case, what we need to show is that both name and ID have been called before we call build for the user identity. And as you can see, the finite state machine has a state for just name, a state for just ID, and then finally a state for build, where any call is permitted. That is, that accepting state on the far right, at that point, it's allowed to call build. And in any previous state, it is an error. And so there's also some sort of trap state or error state. And our static analysis, if we implemented this type state system, would track every builder in the program with a state machine like this, and then issue an error if at any point it discovered a finite state machine in the trap state at the bottom. But the problem with this approach is that, in general, type state analyses are quite expensive. They require the sort of pointer analysis that Manuel mentioned in his talk just a moment ago, which can be very expensive in general. And then they require this for soundness. That is, without a fully precise pointer analysis, it's possible for them to miss errors. And we'd really like to avoid that because we want to be competitive with the compiler when it's checking constructors. But we noticed something about this finite state machine, a sort of a key property here, which is that the transitions here all flow in one direction. And once you reach the build state at the end, the accepting state, it's not possible to get back out into a dangerous state. And this is in contrast to typical or an arbitrary type state analysis, which might have any finite state machine. And so there's no purple arrow like the one that's shown on the screen. And this actually is going to end up giving us a great deal of power. And an analysis or a type state analysis like the one that I'm describing, we call an accumulation analysis. An accumulation meaning that as we transition through the finite state machine, we're only adding additional information about the object being considered. So as you can see, in this case, what we're adding is which setter methods have been called. First, we add the name, then we add the ID. And this particular kind of accumulation analysis, or this particular kind of type state analysis, an accumulation analysis, ends up being very powerful. And the reason for that is that it is always safe to under-approximate an accumulation analysis. So that is, it's always safe to forget some information. So in the worst case, if we lose the fact that, say, ID has been called, we might lead to a false positive in the analysis, but never a false negative. Because once we've reached that build state where it's acceptable to build the object, we would never get out of it. And this means that we can throw away information about aliasing. We do not need the alias analysis or pointer analysis for soundness. And this is a very powerful ability because it allows us to implement this analysis modularly, that is, as a standard type system as opposed to a full type state system. And a type system has a number of advantages. First, it still provides the same kind of guarantees that you would get with the full type state analysis. But no alias analysis and being a modular type system means that it scales much better. Sorry. And we can use all the standard tricks from the type systems literature to reduce the need for annotations and improve performance and so on that you would normally expect. And this leads to a specification for the build method that has like sort of this pluggable type attached to it. You can see this @called methods of name and ID is saying that the receiver object, this object here on the user identity builder, must have had its name and ID methods called. And so this is how our tool actually implements this. And I now just want to give you like a tease for the evaluation that we did, which is fairly large, and you should take a look at the paper if you're interested in seeing the rest. But we evaluated on a particular builder that if a particular field was omitted, would lead to a security vulnerability. And we ran this over about 9 million lines of code. And in those 9 million lines of code, we found 16 vulnerabilities while only issuing 19 warnings. So the other 3 warnings would then be false positive warnings. And then the type system also required very little human work to annotate it. So only 34 places in the program required a human to write an annotation. And so that's it. With this accumulation analysis technique, we are able to get both the best of both worlds between builders and constructors. And we think that this is a really cool sort of subset of type state that might lead to other interesting things in the future. The tool is open source. Please check it out. And I'm happy to take any questions you have. Thank you.
Thank you so much. Very, very nice presentation. So we have one more clarification question. So is there any reason why libraries that you mentioned to create boilerplate methods do not make the method build check required field at runtime?
Yes, so often they do. And I think I mentioned this earlier, I tried to, which is that the best that they can do at runtime, though, is adding a null check that might fail the program, right? And we believe, so a constructor, though, if you had used that approach, would not fail at runtime, it would fail at compile time, which allows the programmer to detect the problem much earlier. And so our goal in this work was to sort of transform that runtime error that you might get in deployment and instead turn it into an error that you get at compile time, like in your IDE.
So we have another question. Does this approach apply only to the builder patterns, or could other patterns benefit from it?
Yeah, that's a great question. So as described here, only the builder pattern is handled, but we believe that this sort of accumulation analysis subset of type state analysis is actually fairly broad. And so we have some other stuff in the works that takes advantage of these properties for other sorts of patterns that lead to bugs. So I'm happy to talk about specifics offline.
So we have last question. Does your approach work well when have nested classes to build inside a given class?
I don't think there's any reason it wouldn't. I'm not sure I've encountered many examples like that, at least in our evaluation, but the technique is a type system. So it's just sort of riding along with the compiler and doing the same type system things that the compiler does. So any place that the compiler is doing type checking, it's going to be able to handle.
Okay, thank you so much. I think we're out of time for this presentation. So our next presentation is by Elias Almawi, and actually, so the name is predictive constraint solving and analysis. This is a near presentation, and this paper won Best Paper Award in your track. So I hope it's going to be quite, it should be quite interesting presentation, and I hope we're going to have many questions from it. So Alice, when you're ready, you can start your presentation.
Okay. Thank you for joining me here. I'm Elias Al-Maawi, a PhD student from the University of Texas at Austin. In this work, we introduce HashCoRat, a new core engine for model counting for imperative predicates. A powerful form of analysis is based on constraint solving, where the logic constraint characterizes the desired property of code and solution to the constraint or desired program state. For example, when the user increases the bound for the bounded exhaustive analysis. So, analysis result for the smaller bound can inform the analysis result for the larger bound. We believe such relationships are a key for a more effective and scalable solving. Our focus is a well-known constraint solver for imperative constraint called CUDA, which has served as a backend for many analyses, include test input generation, program repair, and reliability analysis. CUDA is a solver for imperative constraints. CUDA takes two inputs, the repo K predicate and bound B, which bound the input size. CUDA exhaustively searches the bounded space of candidate input for repo K such that the given predicate returns true for each enumerated input. CUDA uses a baggage tracking search and pruning isomorphisms. CUDA search create candidates by monitoring the field access for repo K that makes when it checks its input. Field access monitoring also allows CUDA to prune part from the search. Here in this example, a binary search tree example, CUDA enumerates 5 solutions. Each is a valid non-isomorphic binary search tree with exactly 3 nodes. The study provides key insight into CUDA search. The constraint solver CUDA finds solutions uniformly once it has performed its initial exploration. We use 10 data structure subjects from the public distribution of CUDA, and we plot the distribution for 2 consecutive sizes, size 9 and size 10 nodes. 6 out of 10 subjects, the lines are almost identical. And for most subjects, line for each size grows linearly after some time, as you could see here. The study provides 2 key observations. First, the solution distribution for a given constraint with respect to a smaller bound k-1 can predict the solution distribution for the given constraint with respect to a larger size k. And the second observation, for size k, behavior of search completed so far could predict the behavior for search that remains. We hypothesized 3 application scenarios for the future work. Predictive model counting, where solution count for size for the desired size k is estimated from the count for the smaller sizes, and approximate sampling, where a desired percent of all solutions is created and used as a test input for the large sizes. Last application, the primitive pruning, where subsequences of steps CUDA search performs are reused during the same search for run. We envision HashCoRat, a new core engine for model counting for imperative predicates. HashCoRat is based on insight into the CUDA search, but it's unlike CUDA, it does not need to enumerate each solution. We believe this work can generalize to tools for propositional logical. In our most recent study, we observed the behavior in SAT solvers, similar to that in CUDA. Our approach is rooted in general principle memorization and incremental method in computer science, which have been employed in many previous analysis and synthesis techniques. Our key novelty is to define an integration of these principles with a focus on internal state of the solver. We believe our work provides promising directions for developing more efficient and effective constraint solving method. Thanks for listening, and I'm happy to answer any question.
Well, thank you so much. So if you have questions, please add it to slide the window on the left. The question I have, so how common those imperative predicates, how common are they, or actually somebody needs to actually type and create them in additional to the code, to the code to be verified?
So CORAT is a text generation, it's imperative constraint text generation and execution. So you need to provide CORAT only with a type of data structure that you want to generate, plus the boundary. And that's what I mentioned. So at the beginning of my slides, the boundary limited by the number of the node for that graph, and plus the type of constraint, which represented by the replica method that checks those constraints to generate those test cases generation.
So we have one more question, but I think we kind of running out of time. So this question will be posted in the Slack account by student volunteer, so you can answer it there. Okay.
Thank you so much.
Thank you. So the next our talk is going to be technical talk, and Matt Lamoth is going to present it. And the talk's name is "When APIs are intentionally bypassed: an exploratory study of API workarounds." Okay, Max, you can take it out from here.
All right, thank you. So as was just mentioned, my name is Max, and I'm going to be presenting my technical paper on intentionally bypassing APIs. This work was done in collaboration with my supervisor, Wei Shang, at Concordia University in Canada. So first, I want to start by saying we posited that some kind of knowledge gap exists between API developers and API users, and this is kind of by design. API developers make the API, and API users use the API, but they normally don't communicate directly through the API. They use other communication channels, and this is done mostly by design, especially for the developers, because their communication can't necessarily scale to all of the users that they have, so they need some kind of indirect communication, such as automated documentation like JavaDoc or wikis, manuals, code examples, whatever you have. But this means that they never directly communicate with each of their users, and it means that it makes it difficult for users to directly give feedback to the developers. So we started by manually observing some communications between API developers and users on forums such as Stack Overflow when we were developing other applications, and we noticed a certain pattern, or at least we thought it was a pattern, so we figured we'd investigate. So we saw that when API users ask things like, that API works in there, but not in here, or I did that with the API, but it doesn't work, or that API used to work, but it doesn't work anymore. These things often end with, is there a workaround? Can I get this to work? So our first question was, do these workarounds exist? And if they do, why are they requested? When are they used? And how can API developers actually integrate these workarounds into their APIs to improve them? So we started by systematically observing Stack Overflow posts with these questions in mind. So we started with a data dump of Stack Overflow posts. There's millions of posts in the Stack Overflow data dump. So we first filtered by just keywords like API, library, framework, and interface, and there were still over 250,000 posts there. So that's very hard to manually observe, right? So we pre-processed some of these using simple means that can be replicated. So if other people want to replicate our steps, it should be very simple to do. We removed code, punctuation, stop words, very traditional NLP things. We keep only the posts with the keywords I mentioned before, so API, library, that kind of stuff. And then we filtered with some trigrams, like I've found a workaround. The trigrams themselves can be found in our paper. I'm just going to mention one here. And even with that, we were still left with 1,846 posts, which is still a lot to manually go over. So we picked the top 400 posts by score. Stack Overflow lets you score posts as you like them. So that was kind of a proxy for popularity. And it allowed us to look at posts that were popular with users. So hopefully would have the most impact if we managed to get information out of them. So we read and labeled them using open card sorting until we were satisfied with the categories that we were coming up with to discover why people were asking for these workarounds and how these workaround questions were being answered. So why do API users ask for API workarounds? So out of the 400 posts, the instances are here. Most of them were because of runtime problems with the API. And specifically, things like unexpected behavior. So let's say scenario 2 no longer works, whereas other scenarios still work without problem. So is there a workaround for that? The people want their scenario 2 to work again. Or backwards incompatibility. This used to work great in version 3 of the API, but it doesn't work anymore in version 4, for example, and then they ask for a workaround. Things like missing desired functionality, we broke down into missing features. So is there an equivalent for get line number for streams in Java 8? Or missing data information in the .NET framework? We can use a specific property, but that property doesn't exist in the current versions. How do I get that information out? Is there a workaround for it? Missing interface. So is this not what the API is meant for? Like I thought this interface would exist, but it doesn't. Is there a workaround? And there were also things like improvements to the API. So like performance or security improvements, and people wanted workarounds to improve the speed or help with API dependencies. People have specific things they want to work with the API and they want workarounds for that. And in 53 cases, the posts were not workaround requests, which could be a flaw on our methodology, but overall we got valuable information out of it. So how are these API workaround requests actually answered by the community? So in 260 of the 400 cases, the workarounds were not supported by the API, or at least that's what the community said. And in 111 cases, people were told this is actually supported by the API. You just have to change your way of actually instantiating the code and you could get this to work. In 13 cases, the user were just said, you're confused. This is not how it's meant to work. Here's how it should work. You don't need a workaround for this. And in 73 cases, it was either unrelated questions or there was actually no answer. So if we concentrate on the not currently supported by the API, we have 5 different main reasons why or how people were told to get these workarounds to work. So either they're told you need to implement a workaround, this will not work without a workaround, you're not confused, this is a problem, here's how you get what you want to work. In 80 cases, they're told use another API. The API you're trying to use is not going to work for this, but there exists another API. You don't need a workaround, just use another API. In 38 cases, the users were told this is not supported, there's no solution, don't bother, even a workaround won't work. In 30 cases, they're told actually, people have complained about this before, a patch is coming, just wait for it, or install the new version, it's going to work, you don't need a workaround. And in 3 cases, they're told there is a workaround, we do not recommend using it, it could cause you massive problems, do not do this. So now that we have this information, how can we use this to actually help API developers? Well, our vision was to take these workaround requests, identify useful workaround patterns from the ones that actually gave workarounds, give those to developers to hopefully improve their APIs. So can we identify patterns, and can we actually find these patterns in actual code after the fact? Because we're still only looking at Stack Overflow posts. So we actually did identify 3 patterns. We named them functionality extension, deep copy, and multi-version. Functionality extension is when users want more out of the actual API than exists. Deep copy is when they're kind of digging into the actual API to extract information to get data, but not necessarily use functionality. They're just using the data to create their own functionality. And multi-version is when they're using multiple versions of the API simultaneously. So we looked at these 5 APIs, Guava, JUnit, Hibernate, ORM, Log4j, and Jackson, and we created a tool to extract these actual patterns from these. And we did it through multiple ways, but basically we look at overrides and extensions for functionality extension, and getters invocations for deep copy. And for multi-version, we look at whether multiple jars are being used for one project. And we found 9 instances of functionality extension, 2 deep copy API workarounds and one multi-version API workaround. We reported these as potential improvements to API developers, and we got pretty good feedback from them. So, so that's my presentation. And if you want more information, of course, there's a lot more information in the paper that I couldn't present today, so you're welcome to go read that. Thank you very much. And if you have any questions, I'm here to answer them.
Thank you so much. Very nice talk. So hopefully people are going to type some questions here. So the questions that I have, do you think those patterns going to be different for different programming languages or different type of applications?
So there is, so first of all, the posts we looked at had no specific languages, but the patterns that we extracted are definitely more object-oriented than, let's say, interprocedural. So, you know, the patterns we extracted are more object-oriented. However, we're not pretending by any stretch of the imagination that these are the only patterns that could have been extracted from our data set. There could have been many more patterns. And in fact, there were other patterns that we saw but couldn't think of a way to identify them. And our data set is available for anyone to take a look and see if they spot more patterns and if they can think of a clever way of maybe identifying these patterns, potentially for other programming languages or even for Java like we did.
Yeah, I think the question that we have is kind of very close to what I asked, but I will ask it again, and maybe you can follow up on it better. So the question is, from the top 400 posts chosen, have you noticed anything common, programming languages, operating system, target user group, etc., in the type of APIs mentioned?
So our data set, which is again open source and available on our GitHub page, has all of the posts identified by programming language. So if anyone wants to take a look at those, they're welcome to do so. We couldn't identify any specific patterns that were language specific, other than there were a lot of Android related posts. I guess those are very popular. And we didn't notice any specific like method or anything that was particularly being called out for workarounds. But we did notice that it was a dominant part of our data set.
Awesome. So we have another question. What is your opinion about the 111 cases in which users failed on identifying the resource in the API?
So actually, in those cases, like already supported by the API is what I assume the question is mentioning. It's definitely due to some kind of communication issue between the actual API developers and the users. Where that communication is failing, I'm not sure, but there have been papers written, not by my team, but I've read those papers that do say that there is some kind of problem sometimes with the users trying to communicate with the API developers. They need some kind of knowledge of internal politics to sometimes get to an actual developer to ask their question. And maybe it's just easier to ask those questions on Stack Overflow where they're going to get a quick answer. So instead of Googling or potentially asking, they're just going on Stack Overflow because they'll get a faster answer.
Okay, so we have one more question. Did you consider the patterns from accepted answers or any answer to the question?
So we specifically looked at accepted answers, and if there was no accepted answer, we looked at the top voted post for the answer.
Okay. I think it's actually it's all the time we have, and so thank you so much. Thank you everybody for posting questions. So anyway, I think there are maybe some people posting questions, so we're going to answer it on the Slack channel. Okay, so basically definitely take a look at it.
Sure thing.
So our last presentation of the session is going to be presented by Zhaju Ren, and the talk is demystifying official API usage directives with crowdsourced API misuse scenarios, erroneous code examples, and patches. And it is a technical talk. So Zhaju, when you're ready, you can start the presentation.
Yeah. Hello, I'm Xiao Xueren from Zhejiang University. I'm glad to be here to introduce my work, demystify official API usage directives with crowdsourced API misuse scenarios, erroneous code examples, and patches. So let's begin the talk. As we knew that Stack Overflow is an open community to help users to get answers to their code questions, developers often look for answers from Stack Overflow. In addition, developers often read API usage directives from official websites. However, what is the relation between Stack Overflow and official documentation? In this case, we would like to link documentation with Stack Overflow. From previous study, many questions on Stack Overflow are caused by developers' ignorance or misunderstanding of API usage directives in official documentation. Let's look at the example from Stack Overflow. Here's a question from Stack Overflow. This is question details. From the answer, we can find the answer that using documentation as answer body. The documentation refers to the code in the question body, from which you can summarize that the correct answer should be use intent flag activity new document instead of intent flag new activity new task. The correct answer also appear in the other answer body, which contains some codes just like this. It can be seen that the documentation often use relatively long sentences to explain the usage of APIs, which can be appear in the answers of Stack Overflow, while some code snippets of answers can deal with problems more clearly. In this case, we motivate to extract error scenarios from Stack Overflow to enrich API usage directives. So here's our framework. The first step is preparing dataset. We extracting API inventory and API usage directives from official documentation and extract the discussion threads from Stack Overflow. The second step is finding API misuse scenarios. We use API partial name to filter out discussion threads. Thus, for each API usage directive sentences, we can get its concerned API and a list of candidate discussion threads. In order to get most relative scenarios, we score all candidate discussion threads using sentence matching approach from macro level and micro levels. From macro level, we use BM25 to compute similarity between API usage directives and its candidate discussion threads. From micro level, we split each candidate discussion threads into sentences, and we use word embedding to compute sentence similarities. Thus, we use a weight of 0.5 to balance macro similarity and micro similarity. Thus, we can get the API misuse scenarios for each API usage directives. After that, we can make further analysis. On one hand, we can select the high quality code examples in questions with regard to the code, the length of code and code relevance and so on. On the other hand, we can use some heuristics to filter out recognized answer, recognized answer, and also select the high quality code examples in the recognized answer. After that, we should match code from questions and code from answers using the method of backup tokens so that we can get the pairs of error news code examples and patch. So that with a combination of API misuse scenarios and error news code examples and patch pairs, we generate our demystification report. Note that our report can just have error scenarios without pairs of error news code examples and patch, which is because lack of qualified answer. For better understanding, we also identify related API and confusing APIs in our demystification report. Let's show an example to explain it. Here's an example of our demystification report. For the concerned API and concerned API usage directives, we find the two API misuse scenarios from Stack Overflow. In the first scenario, the patch is in natural language and it doesn't have related API and a confusing API. The confusing API refers to the API that only appear in misuse error news codes apart from concerned API, and the related API refers to other APIs that appear in error news codes or patch apart from the concerned API and confusing API. In the second scenario, it has both related API and confusing API. To assist developers to understanding the demystification report, we detect and highlight the code differences between the erroneous code examples and the corresponding code patch, just like the purple part. So after knowing our framework, let's show some experiment and the results. We evaluate the quality of each step in our framework to make sure our approach can be the most appropriate one. We adopt a statistically sampling method to examine the minimum number of API usage directives for each type of the extracted information in the demystification report. Two authors independently evaluated the two metrics of the sample data instance. We compute the coherence kappa to evaluate the inter-rater agreement. So for the quality of finding API misuse scenarios, we consider using only BM25 or the word embedding as a baseline. Furthermore, we also use Google search and the search engine of Stack Overflow website as the other two baselines, which simulate the situation when developers search API misuse scenarios for an API misuse usage directive sentence on the web. The Stack Overflow search engine performs the widest in finding API misuse scenarios. It uses very primitive keyword-based search. For the Google search and word embedding search has similar performance in ranking candidate API misuse scenarios, but word embedding has a better accuracy because it has more strict selection threshold. The high MR of the two baselines suggests that the first return results are very likely to be the relevant API misuse scenarios. In construct, the BM25 and our methods perform much better. This suggests that the macro level relevance ranking by BM25 is an efficient method to finding API misuse scenarios. For the quality of erroneous code examples and patches, our approach finding pairs of erroneous code examples and patches by bag of tokens. So we use bag of words as a baseline. This table shows the performance of the two methods. The close MR indicates that the bag of tokens matching and the bag of words matching do not make a big difference, but when looking into accuracy, we find that the bag of tokens matching can be better. For the quality of identifying related API and confusing APIs, our method can almost perfectly identify related APIs. The accuracy identify confusing APIs is also acceptable, but it is more challenging, partially due to the code informatically on Stack Overflow and partially because of vague definition of confusing. After the quality evaluation, we also conduct a user study to evaluate the usefulness of our report. We prepared the 8 tasks to answer, and we rescue 14 people and divide them into 2 groups. The group 1 is control group that are given only the confirmed API usage directives, while group 2 is experimental group that are given our demystification report. We evaluate the participant performance based on their task completion time and answer correctness. The table shows the answer of the results. The table shows the answer correctness of group 2 is better than group 1, and the group 2 can answer the questions faster than group 1. In conclusion, participants suggest that the demystification report can help them in 2 aspects. One is summarize meaningful information to help them find the solution, and the other is enhance their confidence on the answer. Although they have to spend time on reading the report, but nobody complain about this effort. It seems that they consider the help effort the help offered by our report was worth of the time spent. So that's all my talk. If you have any question, you can contact me.
So we do have one question. So this the question is, what is the difference between related API and confusing API?
The confusing API is the API appear in the error code, apart from the concerned API. But the related API is the API appear in the error code or the code patch, apart from the concerned API and the confusing API.
Okay, so I think we kind of already run out of time for questions since your presentation was a bit longer. So I think so thank you so much. It was a very nice talk. So I think we are done with the session. So once again, if you have additional questions, you can post it on Slack channel for this room. So thank you so much.
Thank you.
Thank you.
I think we're done, right?